So far, we've been looking at ordinary rate laws of this form. Rate is equal to K times our reactant raised to some number, which tells us the order of our reaction. And here's it showing examples for a 0, first, and second order reaction. And we know that the K is our rate constant, and its units change depending on the order. So here it's showing the different rate constants of K we can expect. These rate laws are really useful for determining what the rate will be as we change the concentration. So if I double my concentration, how will that affect the rate? If I triple my concentration, how will that affect the rate, etc. But sometimes we don't care about that. Sometimes all we want to know is how my concentrations change over time. And that's where these integrated rate laws come in. Integrated rate laws are great for looking at a reaction and just saying, well, if I start out with 2 molar, how long will it take for me to use up 50% of that? Or if I start with 2 molar, how much will I have after 200 seconds? And allowing us to do a quick calculation to see how the concentration changes over time. We can see that depending again on the order, these integrated rate laws look different. So 0 order looks like this, first like this. This is just a different way of writing it, but it's the same thing. And second order looks like this. So these integrated rate laws just allow us to do a different type of calculation. We don't care about the rate itself like we wanted with these rate laws. Now we're just looking at how concentration changes over time. Now what chemists also like to do is look at this like a straight line. So like a y equals mx plus b equation. And so when we do this, we see that, well, if my time is considered my x and my concentration my y, I can make a graph that looks like this. I can measure the concentration over time, and I can make a scatter plot of that and fit it to a line. And when I do that, the slope will give me my rate constant. So this is another way to get my rate constant. I no longer have to do that method of initial rates. I could just measure the concentration over time and make a graph and get my rate constant out. Now I could do the same thing for a first order. I could still look at it as a y equals mx plus b, but now my y isn't just my concentration, it's the natural log of my concentration. So if I took data where I watched concentration over time, before I made the graph, I would just take the natural log of the concentration, do that on my calculator, and then that's the graph I would make. And once again, my slope tells me my rate constant. Now notice for these two, my slope is actually equal to negative k, but I just have to get rid of the negative, and then I have my rate constant. Same thing for a second order. I can still look at it as y equals mx plus b, but now it's 1 over. So same thing, I would take my data, and then before I made my graph, I would take 1 over the concentration, plug that into my calculator, and I could make this graph right here. And once again, the slope gives me my rate constant. So this is just another way to get out my rate constant by taking data in the lab. But instead of running the same experiment several times with different concentrations and using the method of initial rates, I can run my reaction one time, watch the concentration change over time, and then make one of these graphs to get out my rate constant. So it's just a different way of accomplishing that. Now over here what I have are my half-life equations, and these are specialized equations that specifically tell me what my half-life, represented as T1/2, is. So half-life is just the time it takes to use up half your reactant. So it can be a nice benchmark for how long overall your reaction takes. Some people get a little confused by the way this is written. You really don't need these ones on the right. It's really just writing the same thing twice, so you can just pay attention to this part right here. And for these, the trick is really just figuring out, do you have a 0 first or second order reaction, and then picking the correct half-life expression. So let's look at the type of problem we might have. Example: the following reaction was monitored as a function of time, and a plot of 1 over the concentration of AB versus time yields a straight line with a slope of 0.055 molar to -1 s to the -1. What is the order and rate constant of the reaction? Those are the first two questions. Those are super easy. All we have to do is go back here and ask ourselves, does this correspond to a 0 first or second order reaction? Since the problem specified that 1 over the concentration versus time made a straight line, this must be a second order reaction where the slope is giving us the rate constant. So first problem, really, really simple. What is the order of the reaction? It must be a second order reaction. And what is the rate constant? This number right here. Super simple. From that, we can write all of the rate laws we've learned. The average, our differential one, that's the one where we write rate equals negative delta AB over delta T is equal to positive delta A over delta T is equal to positive delta B. That's a B. E over delta T. That's our average, our differential rate. The ordinary rate law is the one we're doing rate equals, just do rate equals K, which is this right here, 0.055 m to the negative 1, s to the negative 1, and then my reactant is AB, and we said this is a second order reaction, so we get AB squared. So this is my ordinary rate law. First one was the average, this is my ordinary. For the integrated, this is the one where it doesn't actually have the word rate in it. So easiest thing to do is just go back up and we look at the form of our second order rate law, and then we just fill in the blanks with our information. So we have 1 over our reactant molecule is AB, and we put the T there because this one shows that this is how the concentration changes over time. Our K is 0.055, so read, 0.55 m to the negative 1, s to negative 1, T plus 1 over the initial concentration of AB. So this would be my integrated rate law. Now that we have these three equations, we can use at least one of them to figure out the answer to this question. The initial concentration of AB is 0.150 molar. What will the concentration be after 155 seconds? Notice that this doesn't have the word rate anywhere in it. So that's how we know we don't need that average or ordinary rate law. We're going to use the integrated rate laws. Integrated rate laws don't care about rate. They just want to see how concentration changes over time. So I just get to take my equation and plug in my information. So the initial concentration is 0.15. So that's what would go here. And it's asking what will the concentration be, what would this be after 155 seconds? So my time would be 155 seconds. So now all I need to do is go back and plug this in. Oops. So I put this here just so we could remember what my reaction is. And here I see my integrated rate laws, and I'm just going to do the math now. So I have 1 over AB, which is what I'm going to solve for, is equal to 0.055 m to the negative 1, s to the negative 1. My T is 155 seconds, plus 1 over 0.150 molar. Now this whole side I can just plug into my calculator now. Really simple. And when I do that, I get 15.19. My seconds here are going to cancel, so my units, it's a 9 there, going to be m to the negative 1. I have m to the negative 1 here. That, when I do 1 over that, gives me m to the negative 1. And that whole thing is equal to 1 over AB as a function of time. Now, sometimes people will stop here. They're like, oh, okay, I isolated my variable and I'm good, but I'm not done yet because what I have right now is 1 over AB, and what I want is just what is AB after 155 seconds. So since this was 1 over, what I need to do is take the inverse of both sides, raise both sides to the power of negative 1, so that'll turn this into just regular AB. So I'm going to do 1 over 15.19 m to the negative 1. And when I do that, I get 0.0658. And m to the negative 1 over that gives me just m. So after 155 seconds, that's the concentration of AB that I will have left.